Okay, so in this section we're doing what is a basis for subspaces. So in layman's terms is what are the smallest vectors or the smallest vectors we can have that can create the entire subspace itself. And that's pretty much what we're talking about is, think of like the foundation of a house. Right? So what are the vectors that make the foundation of the entire house with all the individual vectors applied to it? Okay. That's pretty much what this is represents. So going through this section, is find all vectors in which all other vectors in the form the entire Rn itself. Okay. So again, what creates it itself. Okay. That's what's called a basis of the subspace. Okay. But before we actually get to how to find those bases, we need a very special definition, something called the spanning set. Okay, so let W be a subspace of Rn, and let S be the vectors W1 all the way to Wm, be a subset of W. We say that S is a spanning set of W, or S spans W, if every vector W in W can be expressed as a linear combination of the vectors in S. Okay, so this is a weird definition. So basically saying, okay, we have this big subspace W, okay, and now we have this smaller set S. We call it the span of S. Okay, now this is called the span of S, meaning it can be blown up to S to all of W if every vector in S is a linear combination of a vector in W, meaning all the vectors in S, if I multiply or add by some arbitrary value, I get every single vector in W. That's what that represents itself. Okay, so hence this is why it comes to this, or in other words, it's linearly independent of itself, okay? Or a linear combination of itself. Okay, so what in the world does this represent? So how does it actually apply, right? So let's say we have two sets, S and U. Okay, these are the vectors S and these are vectors U. And we want to question is, does one of these or both of these span all of R3? Meaning, do these vectors themselves make a linear combination that can create every single vector in R3 respectively, right? So in other words, instead of, over and over again picking out, say this is 1, 5, and 3, right? If A1, A2, and A3 are multiplied by these vectors, do I get all of R3? And same thing applies here. If I'm find an A, B, an A1, A2, and A3, and multiply by these vectors, do I get the entire span of R3, every single vector in R3, right? From the zero matrix all the way to the infinity matrix, right? I guess you guys kind of get the idea. So to do so, all we want to show is, well, does this give us this? In other words, right? Does A sub X give me a V value or a linear combination itself? Okay, so we're going to let V equal the matrix in R3. So an arbitrary matrix in R3. Okay. And we want to solve for that individual portion. Okay, so put this all, well, let's just at U first. So we'll go for the, we'll do U first, yeah. No, actually, so we'll just go this way. So let S, so this is for S first. Okay, all right, so we got 1, -1, 0, -2, 3, 1, and 1, 2, 4. Okay. And these have to equal some vector v, right? So I let it x1, x2, x3. I'll just use A, B, and C for short. I should just use that instead. A, B, and C itself. Okay. All right. And then we just do row reduction to solve for it and see what happens. Okay. So eventually, after breaking this down a little bit into it, we get to our identity matrix, where this side we get these situations. Or actually, yeah, these are right. What was I talking about? This is x1, x2, and x3. Yeah, confusing myself a little bit. Okay, so these are, yes, x1, x2, x3. These are arbitrary here. So instead of A1, A2, A3, I use A, B, and C. That's what we really want. So what does this mean? X1 of this vector is equal to this linear combination. X2 is equal to this combination. And then finally, X3 is equal to that combination. So which A, B, and C are arbitrary A, B, and C here. So it does actually work. So the entire vector of V is a linear combination of X1, X2, and X3. So this will be, yes, it does actually work. Okay. So all we have to do is show basically U does the same thing or not. Okay. All right, so again, after a little bit of work, this ends up looking like this. And I can actually stop here. I don't have to go any further because we get zeros. And after, again, a little bit of work, the right-hand side ends up looking with this combination. Okay, so we do have a bit of a problem because we only have a solution when this actually equals 0. Okay, so what we can say is that U does actually span R3 for any vector. So we'll say, so U spans R3 for any vector V in R3 as long as it's expressed in this situation. So in terms of the span of U equaling any vector V such that this vector V, two dots here, is equal to A, B, C, such that this condition actually holds. Okay. But we kind of have a problem. Okay. Remember, A, B, and C are arbitrary numbers. So the question is, well, again, right, going back to what it means to be a spanning set of W, or spanning set of R3 is every vector can be a linear combination of these. Now we have restrictions, right? This spanning set of U is identified as this, unlike up here where we have multiple situations happening, right? So it's fixed to make it equal to 0, where this one doesn't is fixed. It's fixed arbitrary values we want. So if I want this to be 1, I could fix A, B, and C to make this 1, and vice versa. So the problem is, well, if I have a vector V equaling, let's say, 1, 1, 1, the question is, can I find a linear combination that makes this true? And I actually can't. So again, we have a bit of a problem because vector V is not in the span of U. Okay. So which means this is not a span of R3. So that's the problem when it comes to conditional, right? So you can think of like conditional probabilities if you go back to probabilities, or conditional situations as well. I'm forcing myself for this span to be in a particular way. Now remember, the whole thing is it's spanning to the entire set of R3. So again, every vector must be applied in the situation. And if it doesn't apply, if you can find even one vector that doesn't apply, it's not a spanning set of the entire thing itself. So a bit of a trick question when it comes to the U part itself. So now let's talk about a little more examples of what spanning sets are. Let's talk about the null space. Okay. So let's make matrix A be the matrix, this one, and we want to find a spanning set for the null space of A. Okay. So just in case you guys forgot, that's what it means of the null space, right? So remembering that the null space definition is any vector x that makes this equal to 0. Okay. And that's exactly what we do. So instead of setting it to A, B, and C, arbitrary A, B, and C, we set it to basically 0 because we want to set it equal to 0. And we could find x1, x2, and x3 based off that situation. 1, 1, 2, 3, 5, 4. And again, after a little bit of manipulation, we eventually get this. And I'll change this here to make it look accordingly. So we get x1 is equal to, so x1, x2, x3, so minus 2x3 minus 3x4, and x2 is equal to minus x3 plus 2x4. Okay. So therefore the span of the null space is any vector v such that vector v is equal to, and again now you have two different ways to describe the spanning space, okay, using our vector notation. So we have two independent variables, so x3 is our independent variable, so this is -2, -1, 1, and 0, plus x4, this is -3, 2, 0, 1. Or you can actually give me the actual vectors themselves. So in other words, the null space of A is equal to the span of, and we'll just say u1, u2, where u1 is equal to this vector, and u2 is equal to the other vector. So again, these two vectors themselves span the entire null space of A. Or again, you could write it this way using its independent variable situation. All right. Now let's talk about one more definition before we get to the basis. Okay. So linear independency. So let W be a non-zero subspace of Rn, a basis for W. Okay. So our first, let's say, official definition, a basis for W is a linear independent span set for W. Okay. Now remember, what does linear independency mean, right? There's a lot of things that happen to be linear independency. So I always remember, the easiest one to remember is whenever something's called linear independency, meaning the set equals 0. Or in other words, you set everything equal to 0. Or in other words, you find the null space. Because that's one of the main criteria to what it means by linear independency when it comes to it. So using that definition of what a basis is, right, means they're linearly independent. We want to show, are the vectors a basis for R3? Meaning, do these two vectors span the entire R3, right, of just these simple vectors, right? And there could be multiple, but for now, we'll just choose those 3. Okay. All right, so now we just put them into its matrix format. And just like I give you the hint here, we're going to set it equal to 0 and see. Again, after a little bit of manipulation, and look at this one's already done for us, we do actually get the identity matrix. So remember, linear independency, you set it equals 0, so it's a homogeneous situation. Or remember, another alternative for linear independency is the only solution that actually works is they're all equal to 0, right? If one of them doesn't equal 0, then it's linear dependency, means there's infinite many solutions. So just in case you guys are wondering again why we set it equal to 0, it's one of the other criteria to show linear independency, or an alternative way to showing linear independency. Okay. All right, let's try another example. So nothing now as straightforward. So I don't consider this one a straightforward example. Let R of A be the range of A. So we have the range of A defined to be this situation, where B1 and B2 are any real numbers. So B3 is linear independency of the other two. We want to find a basis for the range of A. Okay, so, well, let's check for linear independency. All right, so we have a bit of a situation here, right? So why don't we split this up a little bit before we do anything. All right, so B1 will be 1, 0, 3 plus B2. This is going to be 0, 1, negative 1. Okay, so our matrix we're going to be dealing with is going to be 1, 0, 3, 0, 1, negative 1. And we're going to see if we have linear independency here, which is probably not going to happen, but we still got to check anyways, right? Okay, well, maybe so, maybe not, right? We can get surprised. So again, after a little bit of addition, multiplying by 3, subtracting it, because this is already done for us. So we actually get this. Oh, look at that. It does actually work. We get our identity matrix, right? So, and since we only have 2's, B1 and B2, it actually does work. Okay? So really, if you want to find the basis, is literally just itself, which is kind of an interesting part, is sometimes the basis for the entire set is actually itself. It's like the mere basis, or in other words, this is literally the foundation of the entire subspace itself. So our basis are the vectors 1, 0, 3 and 0, 1, negative 1. That's it. That's our basis. Bit of an interesting one. Hence why I see this not as straightforward as the other one. Now, the cool thing about finding bases is there's multiple ways to do so, okay, depending on the situation. Okay? So we break it down to about 4 different situations you could deal with. So finding the basis for a subspace W. We could step 1 is, or situation 1 we could do is a spanning set of for a subspace was given. So if this is given, we're done. Solve for the vector equation. That's another way. Okay. The third way is a bit tricky, is if the equation has a trivial solution, meaning all these equal 0, then S itself is a basis for the entire set, kind of like we have here. Okay. And then number 4, so these are pretty much the ones you're going to be dealing with, mode 3 and 4. Very rarely you're going to have 1 and 2. If the equation has non-trivial solution, meaning the equation has unconstrained variables, we delete the vectors that are unconstrained variables, and the rest of the vectors are a basis for W. This one itself is a bit confusing, and we'll do an example of how that's going to work so you can see what I mean by get rid of the unconstrained variables itself. Okay? So don't worry, we'll get into that portion there. Okay? All right, so let's try a couple examples. So let W be a subspace of R4 spanning by the set S of these vectors. So vectors 1 through 5. Okay? We want to find a set of S that is a basis for W. Okay? All right. So we already know this is spanned by this set, and we want to find a basis for it. Okay, so therefore, we'll just use this one, linear independency, the one we've been doing so far. So writing it all into a vector format. Okay. All right, so again, after a little bit of work, this is actually a little bit more work, manipulation itself, so it takes a while. I don't have that much space here, so hopefully you guys could do some more of it in a little bit. We actually get this. Okay. So this is what it means by deletions. We're going to do number 4. So this is a property 4 situation here. Okay. So if the equation has a non-trivial solution, okay, and then we use my pivots here. See, it's already in Euclidean form. Meaning the equation has constraint variables, and we actually do have constraint variables. Right, so again, this is, remember, this is x1, x2, x3, x4, and x5. So we have 2 constraint variables. Oh, sorry, unconstrained variables. Okay. So we have 1, 2, so these are the pivot points, so those are good. We delete the vectors that are unconstrained. So what I'm going to do is just going to get rid of them, okay, and then put the rest together. So if I just delete x3 and x5 vectors themselves, get rid of it, and now we have this. So delete x3 and x5, which are our unconstrained variables. Now we have this. This himself is the basis for it. Okay. So because we have our identity matrix, so it's good. So therefore, x1, x2, and x4 form the basis of this entire W. So the basis is the vectors v1, v2, and v4 of S. These 3 vectors form the basis of the entire set W. So this is what I mean by delete the unconstrained variables. We just get rid of them, and we get exactly what we want. And sometimes we get rid of 3 of them, we're only left with 2. So there are only 2 vectors that represent the entire basis. Again, right, the foundation of what we actually want. Okay. Very interesting theorem going forward. So if the non-zero matrix A is row equivalent to B in Euclidean form, just like everything else, right? Just row reduction to Euclidean form, then the non-zero rows of B form a basis for the row space of A. Now, this only works for the row space of A. That's the trick one, right? That's the key thing. So it's a very particular type of theorem. It only works for the row space of A. Now, the question is, well, how do I find the basis of a row space of A? Well, good question. That's exactly what we're going to be able to do. So how to use this theorem to find the basis of the row space? Kind of done in about 3 steps. Okay. So a spanning set S for a subspace W of Rn will be given to us. That's always going to be given to us, like it is here. Now we'll go to number 2. Let V be an n by n matrix. Okay, so let V be n by basically our matrix associated with these vectors. And we're going to find V transpose first. So we just transpose the entire matrix. And then we're going to row reduce it to find B transpose. So our portion, or in this case, our matrix B here that's at row included form will be exactly that. Okay. And then once we have this, we're going to untranspose it, and the columns of B will be the basis of W. So it's a lot of reversing and engineering using this theorem. Okay. All right, so why don't we just try an example so you can see what the process is of these three steps. Okay. So again, step 1 is given to us, right? We're given a span of S already, right? So now we go to step 2 is we're just going to row reduce it. Now remember, V is the matrix of all these vectors put together. So to do step 2, I'm just going to find the transpose of V. So V transpose. So now everything just flips completely around. So now instead of being a 1, 2, 3, 4 by 5 matrix, now it becomes a 5 by 4 matrix. Okay. 1, 2, 3, 4. Like that. Okay, so once I found V transpose, I now row reduce it to find B transpose. So row reduction here, right? So again, a couple of situations breaking it down, and we eventually get this. So this equals B transpose. Okay. And now we re-engineer it to find B. So we untranspose it. So we're back to a 4 by 5 matrix. Zero. One more zero. Okay. All right, so now this goes back to the last situation, right? So we just get rid of the zero portions because that has nothing to do with it. So therefore, V1, V2, and V3, these, or I'll call them U's itself, but I'll call them different letters. So these are the three matrices, or sorry, three vectors that make the entire basis and spanning these 5 vectors. So therefore, U1 will be the vector 1, 0, 0, negative 9. U2, 0, 1, 0, 4. And then finally U3. So these 3 vectors form the basis for W. So basis is very, very theoretical. It's much more applied portions, and we'll get into much, examples of bases and how these apply. The main ones we care about is, like all the ones we've done, right? The null space is one. The ranges, we'll go into orthogonals later on. But this is just a nice introduction to what a basis fully is, right? Just the foundation of a house, right? How do we find this foundation that built the entire thing itself?